In this video, we will discuss AN+DN mechanism of nucleophilic substitution. For more videos, you can visit us at educationstudio.in. AN+DN mechanism. Here, AN+DN mechanism stands for attack of nucleophile followed by departure of nucleophile. Let us see this molecule. This is the carbon which is connected to oxygen. Because of more electronegative oxygen atom, there is delta positive charge on the carbon and delta negative charge on the oxygen. So when any nucleophile approaches this delta positively charged carbon, it starts forming a bond and the carbon-oxygen pi bond starts breaking in this way. So O has become negatively charged. Now this negatively charged oxygen will start forming pi bond again in this way, and the leaving group would start escaping from the molecule. So in this way L- will be removed from the intermediate. So therefore Nu- has replaced L-. This is called attack of nucleophile followed by departure of nucleophile. Now let us discuss this AN+DN mechanism in detail. This is the molecule. So nucleophile attack the carbon. Carbon-oxygen pi bond is broken. We will get this intermediate. From this intermediate, this is slow step because the attack of nucleophile is here slow rate determining step leading to the formation of unstable intermediate. Then O- will form pi bond, L- will be removed. We will get this. This is reversible reaction because L- is again a nucleophile, can again react with carbon to break pi bond, and from this anion Nu- can be removed back to give the original reactant. So this is a reversible reaction. Important aspects of AN+DN reaction are: more the positive charge on carbonyl carbon, faster will be the approach of nucleophile, which is rate determining step, and therefore faster will be rate of overall AN+DN reaction. Let us see this molecule. This is acid halide, where lone pair of the halogen will have plus R effect. Halogen itself will have negative inductive effect. This is acid anhydride. The oxygen lone pair will have plus R effect here also, but inductive effect of oxygen is less. So therefore delta positive charge will be more on acid halide and it is more reactive than acid anhydride. If we compare acid anhydride and carboxylic acid, the common part is this one, remaining part R, CO and H are different, and this difference will change the extent of positive charge on the carbon. This RCO group has minus resonance effect, negative resonance effect, as well as negative inductive effect. So therefore this electron withdrawing effect of this acyl group will increase the positive charge on that carbon. So therefore acid anhydride will be more reactive than carboxylic acid. If we compare carboxylic acid with ester, this is the common part. The difference is between H and R alkyl group. Alkyl group will be having positive inductive effect. So this positive inductive effect will decrease on the C double bond O part of the molecule. So therefore this is less delta positive charge, and delta positive charge on the carbon of carboxylic acid is more. So therefore carboxylic acid is more reactive than ester. So nucleophile will more easily react with the carbon of carboxylic acid than with the carbon of ester. So this is the order of reactivity. If a nucleophile react on the molecule, pi bond is broken, you will get this carbon N, L minus will be removed again. This is reversible reaction. Now Nu minus can be a weaker nucleophile than L minus, because actually Nu minus has not expelled L minus. Nu minus has only broken the pi bond of carbon oxygen. So therefore any nucleophile, whether weak or strong, can do this process. However, Nu minus should be a stronger base and a bad leaving group than L minus, so that removal of L minus can occur in preference of Nu minus, and therefore the reaction lead to the formation of major substitution product. The rate of this reaction is equal to rate constant into the concentration of RCOL and the concentration of Nu minus, as it is suggested by the rate determining step. So therefore from here you can see the nucleophile is involved in RDS. So therefore higher the nucleophilic strength and the concentration of Nu minus, higher will be the rate of AN+DN reaction. Let us see some molecules. This RCOL, this is delta positive charge. Nucleophile will react, pi bond will break. This will be the intermediate. O minus will again form pi bond, L minus will be removed. You will get this molecule. L minus now can again react with the delta positive charge of the product. In this way, pi bond will be broken, intermediate can be again formed in the backward process. O minus will then again form pi bond, Nu minus will be removed, and you will get back the original reactant. Now if Nu minus is stronger base than L minus, reaction is more favored in forward direction as shown above, and this reaction is almost complete if basic difference is large. Now see another possibility. Nu minus reacts with C double bond O, pi bond is broken, intermediate is formed, O minus forms the pi bond, L minus will be removed. After removal of L minus, we are getting this product. Now there is also delta positive charge. L minus can react back, pi bond will be broken, intermediate will be formed where O minus can again form pi bond, and Nu minus can be removed back, giving the original reactant. So therefore this is a reversible process, and here if Nu minus is weaker base, the process is favored in forward direction. So therefore if L minus is stronger base, the process is more favored in backward direction. So therefore forward reaction is negligible if the basic difference is large. This is side reaction actually, that intermediate anion can take H plus from solvent etc., leading to the formation of this product. So this is nucleophilic addition. So this nucleophilic addition will be the competing reaction while the molecule was undergoing AN+DN nucleophilic substitution. Here it can be generalized that if L is even a bad leaving group like NH2 etc., it can be removed because we were removing it from anions, and we have already discussed when we were discussing leaving tendencies that these strong bases can be removed from anions. However, removal of H minus, R minus, Ar minus is almost impossible even from anions. This is almost a last option. Therefore, AN+DN reaction will mainly occur if that leaving group is halogen, RCOO group, OH group, OR group, or NH2 group, because these can be removed either directly and certainly from the negatively charged ions. But nucleophilic addition, which was side reaction, that will dominate if instead of L there is H, R or AR, as in aldehydes and ketones. because removal of H minus R minus AR minus is very difficult and is almost a last option. So therefore aldehyde ketones will mainly undergo nucleophilic addition. If we discuss the basic strength of those leaving groups, Cl minus is weaker base than RCOO minus, RCOO minus is weaker base than OH minus, OH minus is weaker base than RO minus, RO minus is weaker base than NH2 minus, which are weaker base than H minus, R minus and AR minus. This is the order of basic strength. Now let us see examples of AN+DN reactions. Well-known examples are nucleophilic substitutions in acid halides, acid anhydrides, esters and amides, etc. This is acid halide, delta positive charge on the carbon. If we add RO minus nucleophile, RO minus will react with the carbon, pi bond will be broken. You will get this anion as intermediate. From this anion, O minus will form pi bond, Cl minus will be removed. We will be getting, after removal of Cl minus, an ester molecule. There is delta positive charge on the carbon of ester. Cl minus can react back as nucleophile, pi bond will be broken to generate the intermediate in the backward process. That intermediate O minus will form pi bond, and RO minus can also be removed, because we have already discussed that from anions you can even remove RO minus. So therefore acid halide can be generated back. But because Cl minus was a much weaker base, so therefore the reaction will be almost complete in forward direction. Normally we do not show these reactions by showing the symbol of equilibrium, because the reaction is almost complete. So normally we show it in this way. Let us discuss another example. An acid halide molecule, delta positive charge carbon, OH minus is acting as nucleophile, pi bond will be broken. This anion is formed as intermediate. O minus will form pi bond, Cl minus will be removed. We will get, after the removal of Cl minus, we will get carboxylic acid. There is delta positive charge on the carbon. Cl minus can react back, pi bond will be broken. So intermediate anion will be again formed. From that intermediate anion, O minus, that negative charge O minus can form pi bond. OH minus can also be removed from anions. After the removal of OH minus, you will get back acid halide. But because Cl minus was a much better leaving group, so therefore the reaction is much more favored in forward direction than the backward direction. The reaction is almost complete in the forward direction. Moreover, here proton exchange reaction of RCOOH with OH minus is instantaneous and complete, and will further shift this equilibrium which is shown above in forward direction. In this way, OH minus reacts as a base with carboxylic acid, water is removed, and carboxylic acid is converted to the corresponding salt. So therefore overall process is almost complete in forward direction. Instead of normally showing the reversible equilibrium symbol, we show this reaction by writing unidirectional arrow in forward direction in this way.